Okay, so we're doing optimization, and I just want to give a small analogy to sort of like for you guys to get a sense of what's going on here. It's actually not difficult. You see now, other people think this is the part where it's really, really difficult. It's actually not. So before we would have spoke about functions like, ax cubed plus ax cubed plus bx squared plus cx plus d. Of course, these functions could have been given like something like something like 2x cubed plus 3x squared minus x plus 1. They could have been given by something like that, and this sort of like, the function could have been something like that, like what I'm drawing right now, right? And we'll do all sorts of things. We will find our maximum. So this is our function, right? This is our x. So we'll find our maximum. Where is this function maximum, right? We didn't know what this function represents, but we did it anyway, So we'll find that x value where this function is maximum, and we do that by taking the derivative, setting it equal to 0 to find that one. To find the second one is, that setting the derivative to 0 is probably, if it's a cubic function, you're gonna get 2 solutions, and therefore, this is what we were doing. We know that. That's what we're doing. We're just doing it just in J, We didn't really know what's going on here. Now, in optimization is where we're trying to make something as big as it can or as small as it can, anyone between the two. That's number one. But number two, or maybe number two is that now we're going to start dealing with functions that we know. We're going to start dealing with functions that we know. Okay, I'll just give an example here. I'll give an example. So optimization is the process of trying to make sure that you are maximizing or minimizing the quantity that you're dealing with, right? That's what optimization is. So you would, might have said in the other class that that's what engineering is all about, pretty much. Okay, cool. Okay, I'll make an example here. The example is that we have Mr. Munyai. So Mr. Munyai needs, let's say Mr. Munyai needs to make a rectangular camp with a maximum area, using 250 meter of fencing. So we need to find the area of this camp. Just give you an example. If someone gives you a wire, let's say this is just a wire, and then they say make an enclosure, right? An enclosure, and then you take this wire, or maybe let me put it this way. You can have many enclosures there. You can just have this part and the wire just going around like that, That area is a certain area, but, you can do this to the enclosure, using more wire and so on. And, relative to the blob that I drew up here, you would see that you have made a very much small area in this second example, right? So this is 1, this is 2. In the second one, you've made pretty much small example. So to just have a wire with a certain quantity doesn't assure you that you are going to be giving us a maximum area. So we need to go to some optimization, make sure that we ensure that you will have the maximum area. Okay. That was just an analogy. So let's find a solution to this problem. So the first thing is draw a picture, right? First thing is draw a picture. So he needs to make a fencing, and they told us it's a rectangular one. So he can choose this to be X and this to be Y. That's number one. Just make or maybe I don't know why I would do that, but yeah. Say this is Y, this is X, this is X, this is Y. Anyway. So first of all, just draw a picture. Draw a picture. Number 2, look at your constraint variable. Constraint variable. Now, what's your constraint variable? Mr. Muya, you can make a fencing using 300 meters long. You know, he can't. So the idea of a maximum, it needs to be maximum based on what he has. Otherwise, if there was no constraint, then he could make what is this? A very big area as much as he wants, because he probably, in that case, you would have an infinite number or maybe infinite length of the fencing material, which is not normally the case. When you want to maximize, someone says, this is what I have, can you ensure that I have the best out of what I have? You know, so you will see that Mr. Munya's constraint variable is the perimeter. So the perimeter, he has about 250 meters of fencing. These 250 meters would be used, you know how to calculate perimeter. You must say X plus Y plus X plus Y is equal to 250 meters. So I'm starting here, I'm saying X plus Y plus X plus Y. So I've covered all the sides. So now what we have is 2x plus 2y, and that's equal to 250. Right? That's fine. The third thing that you need to do, you need to set up a function. You need to set up a function in one variable only. Now, when I teach you how to answer exam questions, I'll tell you something. I won't tell you now. Now, for this one, this function that you are setting up, it's the function, this is the function of what you will maximize, or maybe, you know, I was going to say maximize or maximize or minimize. So I'll just say of the function that you would optimize. In this case, ensure that it's the maximum, right? So what are we maximizing here? They say maximum area. So we are maximizing area. So we need to set up an equation for an area. Area is given by length times breadth. And in this case, our area would be given by X and Y. X and Y. X times Y. like that. Are we happy? Because that's a rectangle. Okay, cool. Now I want you to note that they said of one variable, right? They said of one variable. So what we can do now, perhaps I should have done, maybe no. We go to our constraint. We go to our constraint. We said our constraint was 2x plus 2y is equal to 250. So what we then do there, so you can choose here. If you want your area to be a function of x, you can make your area to be a function of x, such that it changes with x. Now you have that y there. So you need to write that y in terms of x, of which you are able to do that. So you would do that by perhaps saying the following. You can divide throughout this equation by 2. You'd have x plus y is equal to 125. And then you can say your x is equal to, or rather, your y is equal to 125 minus x. Therefore, if you go substitute your y there into that function or of x now, you're going to have something like this. Right. So this is the function that you would like to optimize. Yes. So you've set up your equation. Now, this is what I was, or maybe this is the part where I really get excited. Whatever that I'm doing to this function, I know what is this function. I know exactly what it represents. I know how it came about. It's different to just being given an arbitrary function and having to find maximum and all sorts of things. Now I know I'm dealing with a function that represents an area of a rectangular surface, so I know, I'm like, okay, now I can apply my mind now. I can apply my mind into certain things, right? Anyway, now this is given by minus x squared plus 125. Now, I want you guys to understand that you can draw this function, right? You're not going to be required to draw. In fact, let me write it in pencil. You're not going to be required to necessarily draw the function. But I want to show you that at this point, when you start drawing this function, right? This function would look something like this. It's going to be it's going to look something like, no, it's not going to look like this. My apologies. Ooh, let me now think about how is it going to look like. Just give me a second, guys. That would look like, so the intercept one would be at 0, and the other one would be at 125, am I right? Minus x. It's equal to, yeah, I think it would be at 125. So you can try to draw this function. It's gonna have, it's gonna be at 125 here, at 0 here, and this function is a parabola, so it would do this. Or something like that. Anyway, just have the function in mind. So if this is the function that represents the area, your maximum is right there. That's your maximum area, right? But anyway, you're just gonna be like, let me forget about some algebra. Let me just do calculus. How do I find a maximum in calculus? I take the derivative, set it equal to 0, and then you actually do that. That would be 2x plus 125, set that equal to 0, you get that. Now, when you solve that, you will get minus 2x is equal to minus 125. You divide both sides by -2.
I'm sorry, sir.
Yes.
Can I ask something?
Yes.
When you're getting the maximum point, aren't you supposed to derive twice?
No, that's a point of inflection.
Okay, thank you.
Yes. Are you happy with that?
Yes, sir.
Yes. Remember, when we were trying to find the maximum over here, we took the derivative and set it equal to 0. Now, if you take the second derivative, we are here at the point of inflection. And that's not what we're looking for. But thank you for that question. Thank you. Okay, cool. So this is x is equal to, that would divide, and then this is going to be 62.5 meters. And that would be our maximum. That would be the x value that would give us a maximum, right? Now, to actually, now this is one value. You don't have to think about it. You don't have to find the second, you don't have to find, what is this called now? You don't have to find the second derivative to sort of like decide if, is it going to be maximum or minimum, which is normally what happens in your case. When I taught you calculus, I didn't tell you that. Most of the time, you're not going to have to calculate the point of inflection to decide. It's nice if you do it, but you're not going to have to do it. So you put this 62.5 to your original function. Oh, maybe. Sorry. I forgot something here. I forgot. So now you've established this was step 3. What we're doing now was step 4, where we've set up, we're just doing optimization. So we optimize here, right? And optimizing means that you are taking the derivative and you're setting it equal to 0. So that's optimization happening there. Okay, cool. I just forgot to label the steps. And I'm labeling the steps because of the meeting that we had yesterday, where people just say, I get confused what to do, to sort of like show you how you would have to do this. So now you found that the 5th step, which is normally the final step, it's to actually find this maximum area. It's to find the maximum area, the maximum area value, right? By substituting, by substituting into the area equation that you had. So yeah. So your area equation was equal to what? Minus x squared plus 125x. So now you know that your maximum happens at 62.5, and you can then do that. Please calculate that for me and give me what it is. That would be 3906.25 meters squared. Please confirm that. That's our maximum area. Now, that's what optimization is. I'm trying to make sure that we have the maximum that we desire, right? Okay, are you happy? Any questions?
Yes, sir.
Any questions? Thank you for that. I get the yeses for confirming that value, right? Yes. Any questions?
Not yet, sir.
Now, the part that would normally be difficult about these problems is the formulation, is particularly your constraint. It's normally the constraint variable, and also normally sometimes making sure that you rewrite your equation into one variable. That's normally what would be hard. But that's one that we call optimization. right? We also talk about something called rates of change, which is a different application. I won't talk a lot about it, but I'll just, just give you ideas, or probably just do an example. So rates of change is basically noting that if you have a displacement given as a function of time, if you were to take a derivative or a gradient of that, you will get the velocity as the function of time. And if you would take a derivative of that, you will get acceleration as a function of time. And if you take a derivative of that, you get jerk. But we are limited to displacement, velocity, and acceleration. And then you just have to understand what we sort of like doing with these rates of change. So it's pretty much very, very easy for you guys. So let me do some example on this one to do it. So someone comes and say the rocket, someone from NASA says the distance a rocket travels in meters is given by the following function. S is the function of t is equal to t cubed minus 1. But guys, do you really appreciate the idea now that we're talking about functions that we know? With the time in seconds. That's our example. Now we can ask you sorts of things for this one, right? We can ask you the distance the rocket traveled after 5 minutes. So we can ask you the distance the rocket traveled after 5 seconds. And then to answer that, you would then have to say, this is the, this gives us the distance. So if I evaluate the distance formula at 5 seconds, or the distance function, then I would have something like this, which should be 125 minus 1, I suppose. So it should be 124 meters. And then I can perhaps ask you, number 2, the average speed of the rocket between 5 and 10 seconds. The average speed, right, of the rocket between 5 and 10 seconds. So they want the average speed. So the average speed, you guys would remember from, I don't know how to sort of like explain this, but the average speed, between 5 and 10 seconds, it's kind of the same as average gradient. So you just like, let me do it that way actually. You're just like, oh, okay, they want between 5 seconds and 10 seconds. Let me go check what is my function at 5 seconds. Now I know my function at 5 seconds just from the calculation above. It would have traveled 124 meters. 124 meters. Which makes your coordinate, your first coordinate to be 5 seconds, 124 meters. And then you say for this one, for 10 seconds, you can substitute the 10 cubed, that's 10,000. And so this is 999, because 10,000 minus 1. So, which means that your second, what is this thing called? Yes, your second coordinates would be 10 seconds and 999 meters. And they want the average gradient between those, and then you can just say, they don't want, yes, they want the average gradient, but it's actually speed. You can say speed average, and then it would be change in sort of like S, which is the distance, over change in time, which is the time. So you don't just change in Y divided by change in T. You know what you're talking about now. So you can't just use any, things randomly. So you can say 999 minus 124 divided by 10 minus 5. And if you put that in your calculator, you should get 175 meters per second. Now you must note that the unit at the top is meters, the unit at the bottom is seconds. Right. That's one way you can do it. That's one way where you actually understand what you're doing. I guess in this, doing it this way, you more like understand what you're doing. Or you can do it a bit differently. You can just say that my average speed will be equal to S10 minus S5 minus 10 minus 5. And it's pretty much the same thing, but this one follows the idea of f of x plus h minus f of x. And when we're trying to, before we took the limit and we said this is our average gradient, before we took the limit and we said this is x plus h minus x. If you remember that, I'll just put it there. It was before we took the limit, we said, okay, this is the average gradient between 2 points. And then before I say, okay, now let's go take the limit, before that idea of taking the limit, that's, you can use that intuition to sort of like come down to the same value, 99 minus 124 divided by, suppose 5, and that would give you 175 meters per second. Okay, right. So this one highlights a lot about what we've done so far in calculus. That's why I kept using the physics kind of interpretation about why we need calculus. Now, the third one, it's called, they say, find the instantaneous speed at 8 seconds. So they want to know exactly what the speed of the rocket at 8 seconds. That's like the gradient at a point, right? Right, so it's a gradient at a point. So it's the same as just the derivative. So it looks like they want the derivative here. The speed here, if it's instantaneous, then it's the derivative. The derivative would be, for this particular function, it would be 3t squared. Oh, why am I putting x here? Thank you. T, and then they want to know what's that at 8 seconds. So that would be 3/8 squared. And that would be what? You want to confirm that for me? 192 meters per second. It's speed as well. Now, number 3.
Yes, sir.
Thank you. Number 3, they want to know what's the acceleration. What's the acceleration of the rocket at 12 seconds? At 12 seconds. It's the acceleration of the rocket at 12 seconds. And that one, you must know, you must take the derivative of the gradient, or the derivative of the derivative, or just the second derivative. Second derivative there, it looks like it would just be 6t. They want to know after 12 seconds, Please do that for me as well. 6 times 12, would that be 72? Meters per second squared, it's acceleration. So these are the two applications. Are you happy with that? Are you confirming that?
Yes, sir.
Thank you. These are the two applications that we have. You know, these are the two applications that we have. There are other applications, just that you guys don't do it. We do related rates.
Sir,
yes.
why are you saying F and not S to the
Yes,
S?
that's correct. I'm just used to F. Thank you. I'm just being used to F.
Sir.
I think the way I'm so used to F is crazy. Yes, thank you so much. That's very correct. Yes. Happy?
Yes, sir.
So I'll just do one question from the chat. I'll do number 1 for you guys. Just on examples. So suppose you're given a right angle triangle, LUV. Ooh, you guys can see. Okay, I must draw. So you're given this guy. This is number 1 from the chart. This is 10 minus x and x plus 2, right? They say given a right angled triangle, right? The triangle is actually named LUV, but I'll just say that given a right angled triangle, you're given that UV is equal to x plus 2. You're also given that LU is equal to 10 minus x units. Then the first question is just to say, determine the area. So they say determine the area of this triangle.
So isn't it going to be half base times height?
Yes, so the area is half base times the perpendicular height. So that would be half, your base is x plus 2, your height is 10 minus x. So now your area is half please calculate that polynomial, that thing inside there.
Yes, I'll calculate it now.
Yes, that should give me 10x minus x squared plus 20 and minus 2x. Okay, cool. Please confirm. That would be minus x squared plus 8x plus 20.
Yes, sir.
Cool, that's the area. At this point, I do know that my area is a function of x, so I would like to write it as the function of x. And then the last question, it says, calculate the maximum.
Sir?
Yes.
Don't forget to calculate with the half as well.
Oh yeah, I just leave it outside.
Oh, okay.
Yeah.
But is it right if you continue?
Yeah, you can put it this way.
Like negative a half x squared plus 4x plus 10.
Yes, you can.
Yeah.
And then yes, that was determine the area of, yes, we've determined the area. Number B, it says calculate the value of the x for which we will get a maximum area, right? Oh, sorry. This is value of x for a maximum area. So we take the derivative of that, we set it equal to 0, simple. That would give us minus x plus 4. Take the derivative, set equal to 0. You get a mark for that. You must always write it down. So that's minus x plus 4 is equal to 0. So your x is just 4. That's the x value that would give us a maximum. Now the last question says, which is C, we must find that maximum area. So we just put the value of x that would give us a maximum area over there, and then we calculate. Guys, I think this is actually not bad, is it? Is it bad? And then, can you please do that? Is that, substitute that for me and calculate it. That's 10 plus 4 times 4, that's 16. So that's 26. Minus 8, 26.
Is it 18?
Yes, looks like it will be 18. The maximum area, we're given units there. So this would be units squared. This would just be units and so on. Are you following?
Yes, sir.
Okay, so in class, I'll probably just do number 4 as an example, right? And yeah, so from now on, we're gonna be running 2 classes at the same time. We are gonna be doing, the next chapter that I'm doing for you tomorrow is patterns, but you're also gonna be doing functions at the same time, right? We've explained that yesterday, right?
Yes, sir.
Okay, cool. If you are happy with that, I am happy. And then I'll try to make sure that you don't have as much load. I don't want you guys to break down. So
Yeah.
so the assignment is due Sunday now.
Yeah.
And the tutorial that was due yesterday is due by today, but you can submit it tomorrow.
Okay.
Yeah, let me just say it's due tomorrow. I don't want you guys to not be able to learn. Because when you have a lot of stuff to do, you end up not learning and just doing the stuff.
Yeah.
Okay, that's it from me. You can join the class in the evening if you want, but yeah, that's it.
Yes, well, because today I'm not getting physics.
Okay, that's good.